Hello guys, in this section I will talk about you guys about the Venn diagram of p-n junction and morely when equilibrium state, when the bias VA applied, how to change the Venn diagram we will to study in the next section. First, I will talk about how to draw some Venn diagram. First, in equilibrium state, we will first draw some variable level constantly because it is equilibrium state. And we will draw the balance band. First, there is a narrow gap of the variable level and balance band, and there is some large gap in variable level and balance band. So we will draw some balance band, and this is an equilibrium state. So the gap of the variable level and balance band's gap, it may be same to about apply some conduction band. So the gap of the conduction band and balance band will be same. So we will move on above to draw some conduction band. So we can draw this in conduction band diagram in equilibrium state. We will draw the band diagram, but if we see the site of charge state, we can know this state is the same state. First, when the conduction band is variable level, the gap of two states is very smaller, then it means the total concentration is very high. So in this section, there is so many concentration and charge electron will be exist. So in this section, there must be exist the donor plus charge of donor, and the electron is very high density of concentration. But when the x-axis goes up, the conduction band and variable levels gap is getting higher, getting larger. That means the concentration of the electron will be really smaller exponentially. So in this section, there must not be exist the electron, maybe very smaller. So there's a very smaller charge electron will be exist. And this also makes sense in balance band. So in this position, there must be really many holes, but when the variable level and balance band's gap is so getting larger, then the plus hole will be smaller. And in this position, there is some plus charge hole and electron will be recombination. So in this position, it only left is plus charge of donor and minus charge of acceptor. It is only a fixed charge. So we can talk this section to depletion reason. And after we draw some band diagram, we will talk about when it gets some bias. First, the black graph means equilibrium state. When the p-type semiconductor, when anti-semiconductor get minus charge and the p-type semiconductor get some plus charge, it means forward bias. And when reversely, when n-type semiconductor gets some plus charge and p-type semiconductor gets a minus charge. It means reverse charge. When in energy band, the site of energy band, when the anti-semiconductor gets a minus charge, the energy band will be getting up. So we can draw the conduction band up energy band, and when the p-type semiconductor gets a plus charge, the energy band getting lower. So we can draw, when the force bias, we can draw the band diagram like this red graph. It means the junction voltage will be getting smaller than the equilibrium state. In this case, when the first charge getting some anti-semiconductor, it means the energy band gap will be lower. And the p-type semiconductor gets some minus charge, the energy band getting up. So we can draw the new red line graph. It means the reverse bias and force bias, the junction voltage will be smaller and larger. Totally, I will talk this total graph in new site of Boltzmann tail. In equilibrium state, we will draw some Boltzmann tail like in this. Sorry. Did you guys understand in this graph? Sorry, I'm not good at drawing. First, when the upper energy between of the conduction bands more than conduction band energy in this position, this type n-type semiconductor's electron can move on p-type semiconductor more easily because the energy is more higher than p-type semiconductor. But when in this position of energy, electron can't move on to p-type semiconductor. It's more harder than this state of electron, because in this section it must be exists the electric field, and electric field we're getting in this direction. So the electron will be moving in this reverse direction. So if this electron getting to p-type semiconductor, it's more hot. So in this case of electron will be goes up to this Boltzmann tail. But in this position, there is a barrier. So this electron gets harder to move on to p-type semiconductor. We will apply this Boltzmann tail knowledge into the bias applied. First, when the junction voltage is getting smaller, in this case of forced bias, the Boltzmann tail will be and this position will be more easier to go up to anti-semiconductor to p-type semiconductor. But in this position, it is harder to go up to p-type semiconductor. And we will see about the difference about equilibrium state and the force bias state. The more easier position to move on anti-semiconductor to p-type semiconductor. The total state is more bigger when forced bias get in this state and in this state. We will compare. In this state is more easier to move on to p-type semiconductor. And this state, we'll compare in this state, and the equilibrium state is more harder to get up to p-type semiconductor. So when we get forward bias, the electron in anti-semiconductor is more getting easier to get to p-type semiconductor. Understand? Then the reverse bias case is maybe more harder to get some anti-semiconductor to p-type semiconductor because the junction voltage is higher. Thank you.